Hello everyone, this is the video for the Algebra 2 end of course review for Chapter 3, and we will be talking about cubic functions. Okay, we're going to start by drawing the parent function for x to the power of 3. So you're going to start with a basic x and y axis. You're going to have this little turning point right here in the middle, and it's going to have this kind of up roller coaster top pattern to it. Now, if you stretched it vertically, it could look something a little bit more like this, to where you might have this kind of thing going on. But this is basically what it looks like. The domain and the range are going to be all real numbers. There's no limitations. So before we get into just cubic functions, let's take a little quick review of what each type of polynomial looks like up to Chapter 3. So the first one would have a degree of 0. That's called a constant. The reason why it's a constant is because it does not have a variable. That is going to look like a horizontal line when you graph it. The second one is 1 degree, or your first degree, which is linear. It's because you have x to the power of 1, and that's typically y equals mx plus b. Chapter 2, we talk about quadratic, which is x squared, and that looks like a smiley face when you graph it. And then on to cubic, which is a third degree. It's going to look like a coaster pattern. So either up coaster, or if it's reflected, a down coaster pattern. The good news is that all of your transformations are the same as in Chapter 1 and in Chapter 2. So if you add or subtract from the x, you go left to right. If you add to your function, you go up or down. Negatives are going to cause a reflection, either over the x or the y axis. If you multiply to the x only, it's going to be a horizontal stretch or shrink. And if you multiply times the whole function, it's going to be a vertical stretch or shrink. Something that they could ask you about on the end of course is end behavior of any function, but let's talk about cubic functions in particular. So if you wanted to write the end behavior of a cubic function, what you would do is focus on the end points. So this one doesn't actually stop. It keeps going forever in either direction. So if you look at this notation right here, it says x approaches negative infinity. That means to the left. So as this function travels to the left, what it does is it also goes down. So when it says f of x, it means your y values are going to go down, which is negative infinity. Same thing over here on the right. It says as x approaches positive infinity, that means that it is going to the right. And as this goes to the right, it also goes up. So it's going to reflect with that positive infinity. So let's look at a down coaster pattern. So down coaster pattern looks like this. You're decreasing, and then you increase, and then you decrease again. But if we're talking about end behavior, all we want to do is focus on the arrows. So the left arrow, as x approaches negative infinity, goes up. So it will be positive infinity. The right arrow, x approaches positive infinity, goes down. So y would approach negative infinity. Let's talk about the relationships between the zeros, the factors, the solutions, and the x-intercepts. One thing that you do need to understand is that solutions are not factors, but solutions are zeros, and solutions are also called roots. So if they want you to solve or find the x-intercept, that's what you're going to do. You're going to find the solution, the zero, or the root. Okay, so this little tidbit right here basically says if k is a zero of the cubic function f, it is going to be a root or a solution. So let's say that you have a solution that is equal to 5. That is a root, that is a solution, that is a 0. Now, if you know that x is equal to 5, then you immediately know that x minus 5 is a factor. See how the factors are different from the solutions. If you know that 5 is a solution, then you know if you plug in a 5, you get 0 when you plug it in, because it's going to be an x-intercept. So the coordinate would be x is 5, y is 0. That's why when you substitute 5, your output is 0. And that brings me to the factor theorem. So this one is going to work several different ways. Like if they straight up tell you, like, you know that something is a solution, then you can immediately say that if you plug in 3 into that function, you will get a 0 back. That means you have no remainder. That means when you graph it, you're going to have a coordinate of 3, 0. They could also tell you that you might have a factor of x plus 2. What you have to do is you have to realize that x is equal to -2 would be your solution. Therefore, if you plug in a -2, you're going to get 0, okay? So if they go backwards, if they say f of 10 is equal to 0, then you can therefore say that the solution is 10 and a factor is x minus 10. That is the factor theorem. Okay, so let's take a second and talk about cubic regression. So if you have points and you realize, now they're not going to be scattered like this, but if they're kind of scattered in kind of a roller coaster pattern, you can use a regression to estimate that pattern. You're going to do the same thing that you do in all of the other regressions. You are going to type in that table into Desmos. You do that by clicking that plus sign and then adding the table. On the second line, you're going to type in a really long code. Just make sure that you use y1 and x1 and the tilde. If you don't use y1 and x1 and tilde, it will not compute the regression equation for you. So you're going to use the standard form of a cubic equation, and you're going to substitute the a, b, c, and d, and then make any predictions if they ask you to do that. And the last thing on the front page is basically talking about first differences and second differences. This is an example of how your first differences are not the same. If your first differences were the same, it would be a linear equation. If the second differences are the same, and these are, it would be considered quadratic. Okay. If your quadratic second differences are not the same and you continued on and you found that your third differences are the same, the third differences are going to be cubic. Okay, just in case that pops up. Okay, let's do some practice problems for chapter 3. So the first one says if x plus 2 is a factor, right now, immediately, if it tells me something is a factor, then I immediately know that x is equal to -2. I also know that if I plug in -2, my answer is going to be 0. And guess what they asked me to do? They asked me to plug in -2. So honestly, this really doesn't matter what that is. As long as that's a solution, it is going to produce a 0. So immediately C. All right, so the first part didn't really talk about factoring. It's just something that you need to know how to do, and it's very difficult to summarize in like a tiny little square. So let's talk about it here. The first type of factoring you want to know how to do is greatest common factor. So if you look at your numbers and look at your variables, you can see that we have a 6 in common and we have an x in common. So the first thing I'm going to do is factor out a 6x, and our leftovers are going to be x squared minus 7x plus 10. I can see that this one could possibly be factored one more time. I'm going to use 10 and -7. Factors of 10 are going to be -2 and -5. So I'm going to wind up with a final factored form of 6x, x minus 2, and x minus 5. If it asks you to solve, you're going to take it one more step, and you'll say 6x is equal to 0, x minus 2 equals 0, x minus 5 equals 0, and solve. So your GCF is going to have a solution of 0, this will have a solution of 2, and that will have a solution of 5. That is only if they ask you to solve it. This one, on the other hand, this is going to be a lot more complicated because what you have to do is recognize that's a difference of cubes pattern, and you need to write them as cubes. I'm going to show you how to do this right now. So that is going to be 2x to the power of 3, and this is 3 to the power of 3. What this does is it gives you the first factor. So immediately I know my factor is 2x minus 3. Here's where the hard part comes into play. You've got a 2x and you got a -3, and you're going to divide that into your first term, and your first term is 8x to the power of 3. So work backwards. So that'll be 4x squared, and then multiply. Didn't leave myself enough room. Here's the thing. Your diagonal has to add up to what you're dividing into. I do not have a square, so I'm going to cancel that out by writing positive 12x squared, and then I'm going to go backwards again. So that'll be 6x multiply. Once again, I don't have anything that's linear in here, so I have to cancel that out by putting 18x. And then it's going to be 9. And if we've done everything correctly, this last number here should match this, and it does. Okay, so final answer, let me scoot this over a little bit. It's going to be 2x minus 3 times my quotient. And that's how you factor it. Okay, for our next example, we have a baker that's making a birthday cake, and he's stacking the cake layers on top of one another. Each cake layer is a rectangular prism. So eventually what it's going to want us to do is find the volume of each layer, and this is the formula for the volume of a rectangular prism, length times width times height. So I'm going to go ahead and I'm going to find the volume of one of these layers of cakes. So it'll be 2x times x times x minus 8. Now, I'm not going to multiply that out just yet, because if you look at your choices, it seems like some of it's multiplied and some of it's not. I'm going to go ahead and consider the fact that I'm going to have 3 of these cake layers. If I have 3 of them, that means I'm going to take this right here and multiply it by 3. I'm going to try something. So it looks like the first few have been multiplied together, so I'm going to do that. 3 times 2 is 6. X times x is x squared. And does that match anything? It does. Okay, so if your question is multiple choice, just kind of look at the answers and see if you can manipulate it to match the answers. Okay, so the next question says, is x minus 3 a factor? Now, if you know that you're looking just for a yes or no answer, you can simply just plug in a positive 3. If you get a 0, then it's going to be a factor. But unfortunately, it is asking me to find the remaining factor. So the only way that we're going to do this is to divide this polynomial by x minus 3. So this is very similar to the question above it. You're going to start with x to the power 3, and you're going to work backwards. Okay, remember your diagonals need to match what you're dividing into. I don't have an x squared term, so I'm just going to cancel that out to make it 0x squared, and then work backwards again. This time I do have a linear term, so this needs to add up to be negative 15, which makes that 6x. Now, if I multiply all those correctly, I should wind up with a positive 18. So absolutely, it is definitely a factor. So no is not an option here. And my factors are actually what I came up with. X minus 3. These are all the same. And then this is how I'm going to figure out the answer. So the answer is B. All right, so I got a little head start on this question right here. It gives you a table of values. It does not show you what they look like, but it does tell you it shows a cubic pattern. So I went ahead and typed the table of values in here. What's really neat about this, if you do the table, if you want to see all of your values, just click the little plus magnifying glass and it will zoom fit. And as you can see right here, let me scoot it over just a little bit. It does have that kind of up coaster pattern to it. So this is ideal for a cubic regression. And if we want to do a cubic regression, we're going to type in y1 tilde. So we're going to do ax. Every time you do y or x, make sure you put a 1 next to it. But it's cubic, so it'll be to the power 3. This one would be squared. And then you're going to add d at the very end. I always forget to put my 1 next to that last x there. Okay, so right now I can just tell what my a, b, c, and d is going to be. I'm going to write that down, and then we're going to plug it in and see what we get for 10. Actually, you know what? We can just do that right now. So 10 seconds. I'm going to just kind of click and drag until x is 10, and there it is. So if you plug in 10, you're going to wind up with 35. So you can do it that way. That's the easiest way since I have access to Desmos. So I'm going to say 35 is my answer here. And if I wanted to write this out, I'm going to do y equals, and then I have to look at all of my values over here. So that's 0.001. And then negative 0.12, 3.6, plus 10. And there's how you do your regression. Okay, and for the last question on chapter 3, we are looking to see what best describes the function when x is greater than 5. So what you need to do is you need to locate 5 on your graph, which is right here. And you need to look at only the part where it is greater than that. So that is this little section of the function. It's going to ask you whether it's positive or negative. It is above the x-axis, so it is positive, and we are heading up. That is an increase. So it's going to be positive and increasing, and that's all for chapter 3.